Hi everyone, welcome back. We are going to look at some data and we're going to try and identify the best model for this data. So the table below shows the US plastic bottled water sales in billions since 1996. Now that's really important because when it says 1996 here, that is implying that you are starting with 1996 being time equal to 0. This is for mathematical calculation purposes because if you don't set it to 0, then you're basically starting from t equals 0 and then calculating 0 until 1996. That would be weird. So we're starting at time equals 0 in 1996. So this would be 0. 2 years later, we're at 1998. 4 years later, we're at year 2000. 2002 would be 6 years later. 2004 would be 8 years later. And 2006 would be 10 years later. So our data is given in specific years, but we start calculating at time 0 in 1996. I hope that makes sense. Now remember, the number of bottles sold are in billions, but we're going to just remember that it's billions and not make that additional calculation of many, many digits afterwards. What type of function will model this data the best? Well, it might not be obvious from looking at this, but if you look at the distance from 3 to 5, that's 2. From 5 to 8, that's 3. From 8 to 15 is 7. And so it's clearly not linear. It may be quadratic. It may be exponential. You could calculate 36 divided by 24 and then take 24 and divide it by 15 and see if these numbers come out the same. And when I do that, they do not match. So we do not have an exponential growth here, but we could probably model it with exponential growth even though it's not a perfect exponential growth problem. So let's go ahead and do that. I'm going to say that it's exponential, and then we'll calculate the equation that would best model this data with an exponential function. And look at that, it tells you to do it that way. So let's go ahead and calculate or enter those data points. So we'll turn our calculator on, we'll go to y equals and clear our y equals out, we'll go to second stat plot. We'll make sure it's on. We'll also go to quit and then clear anything in our main home window. Now remember, we first go to stat and then enter, and we have two lists. If you have new data to enter, you clear the lists that are there and then hit enter. So we'll go up to list 2, hit clear, and then enter. We'll go over to list 1, arrow up so you're on list 1 and hit clear, enter, and now your tables are cleared again so you can enter this new data. Our X values are 0, 2, 4, 6, and 8. And 10. And in our second list, list 2, we have 3, 5, 8, 15, 24, and 36. And just to make sure that you've done all of your calculations right, your list 1 has the same number of entries as your list 2, so you're good to go. If we want to create an exponential model for this data, we would go to stat, calc, and then arrow down to exponential regression. Click enter, double check that list 1 and list 2 are indeed correct, and then we arrow down to calculate and hit enter. This is our data that we would use to find an exponential function that would hit these points best. And so now we go to y equals. In y equals, we click variables, go down to statistics, or just click 5, hit enter, and then go over to EQ, which stands for equations, and see how we have reg EQ, that means regression equations. Click enter, and it automatically populates that data into the y equals equation. And now we just hit graph, and you can see how our regression calculator has made a beautiful exponential curve that hits our data points quite nicely. Now it doesn't look like all our data points are represented here, so let's go to zoom and arrow down to number 9, which is zoom stat. Click enter, and now it gives us all the data points in the window. And you can see how the curve is doing a great job of approximating the data given. Now, in our scenario here on the handout, we're asked to round a to the nearest whole number and b to 4 decimal places. So let's go ahead and look at the equation here. We had a is 3.027, etc., but we want a rounded to the nearest whole digit, so a equals 3. And now let's look at what b is. B is 1.2887, etc. We want to round this to 4 decimal places, so that would be 0.28878. 8 is larger than 4, and so we have to calculate this as 1.2888, and that is your base B. So we want to now talk about what A and B represent in everyday language. Well, A represents the initial amount of bottles being consumed. 1996, 3 billion bottles were being sold. And B means how quickly it's doubling. So the base is 1.2888. So that is the percentage increase. So 0.2888 is how much increase is happening each year. So 28.88% increase per year. We could say with this much. So that's how fast it is increasing, or how quickly it's increasing. Find the water bottle sales in 2010 using this model. All right. Well, if we had 2010 and we started calculating in 1996, that would be 4 years from 2000, so 14 years later. So T is now 14 years, and that's our input. So our output, f of 14, is equal to 3 times 1.2888 raised to the 14. And we can do that in our calculator. 3 times 1.2888 raised to the 14 equals, and that's a lot, 104 billion bottles. If we rounded, it would be 105 Or we could just say 104.6 billion. Bottles sold. So that's a lot. When will the U.S. water bottle sales reach 150 billion? Well, now it's not giving you the years since we started calculating. It's now saying how many bottles will be sold, and then you reverse engineer it to figure out what year that would be true. So 150 billion is equal to 3 raised to the 3 times 1.2888 raised to the x, and we need to figure out what x would be. Now, this would be something better done in your calculator, since we haven't talked about solving logarithmic equations here. So let me show you how you can do that on your calculator. You'll go to Graph, and now we're going to click Trace. And hopefully you can see this little cursor. It kind of looks like a spider crawling up the graph. So if you arrow up or down, it will hop between the data points or the curves. And now I'm just going to scroll until y equals 150. And notice that it stops when my window is at a certain point. So I'm going to zoom out. I'm going to hit trace again. Just make sure that I'm actually on the curve. There we go. And I'm just going to keep going to the right. So I'm almost there. So 158 and the previous is 139. So see that between 139 and 158, it's still in the same year. It looks like 15 years. So 15 years from 1996. That's a very detailed question that took quite a while, but I was explaining it along the way. So hopefully with some practice, you can become very confident with how to use your calculator or an Excel spreadsheet or Desmos to calculate this regression.